Hello, I'm Marilyn Ibarra-Caton. This is my presentation for the final project for predicting electrical and energy output. And the modeling approach that I took, started with linear regression, which I was familiar with, and then I wanted to do the other models which were newer to me, the random forest, the cross-validation from fivefold, the decision tree, and the neural network. In the model evaluations that I did, I wanted to try two. One that I was familiar with, the R-square, which measures the percentage change in the variation in your output from the change in your features or your x's. And then the root mean square error, which I was not familiar with, which is the average deviation of the predicted values from the actual values, or measures the average deviation of predicted values from the actual values. And let me just show you quickly my Python code. I did all this in Python, which I have some experience working with. So I split the data. I did train the linear regression model. I plotted the scatter plot of the actual versus predicted values. Then I did the cross-validation of the k-fold performing 5-fold cross-validation on the training set. Then I did a random forest regressor that was similar for the cross-validation. Then I did the decision tree, and I thought it was really cool to do a visualization of the decision tree. So I included that. And then lastly, I did the neural network, and you can see here the two outputs that I used, the root mean square error and the R-square. So that gives you an example of my Python code. And here's some of my output. My output is the linear square regression, gave me a RMSC of 4.5 and R-square of 93, and here's the plot of the actual versus the predicted values. Did okay, but when you compare it across the other ones, it wasn't the best model. Here's a little bit of what I did for my model building. I used for the initial models comparison, I did a det of 3 and 100 number of trees in the forest, and I used changes in these hyperparameters later on to see the performance of the models. The cross-validation, and let me just, before I get to that, here's a sample of my output in Python, the 4 features that I used, and how it broke down the training and the test data. So for the cross-validation, using a 5-fold, here's the RMS scores. It gave me the mean of 3.46 and a mean square of of 95%, which actually performed much better than the linear regression. When you look at the random forest, the 3.24 and R-square of 96%, which is slightly, the 3.24 is slightly lower than cross-validation mean. The R-square is higher, which means that the model is performing well on the test data relative to the other models. And then when you look at the decision tree, the RMS of 5.16, that's much higher than the random forest, and the R-square was actually the lowest of all the models. So then I did some model changes. I left the split data per 80-20 the same, but I only changed the hyperparameters for control the tree depths, and then the number of trees was changed. And let me show you what that looked like. So the first one that I changed was the det at 10, and the random forest pretty much stays about the same. The decision tree, that jumped from about 90% to about 94%, so it's doing a little bit better. Then the next change I did is change the number of trees from 100 to 500, and the random forest slightly improves, but pretty much stays pretty constant. The decision tree also improves there. Then the last thing that I tried was a det at none. The random forest stays pretty stable, and the decision tree, the performance drops slightly there. And the last model that I looked at was the neural network model with the RMSC of 5.2, and this was better than the decision tree, but not better than the linear regression, random forest, or cross-validation. Actually, it's a pretty bad model. The R-square was always, given the different hyperparameters, I won't show you all the results, but it was always in the 80-ish percentile. So in summary, the random forest achieves the best prediction performance of all the models.